Hello everyone, so my name is Blythman, and today I'm going to be presenting on behalf of our team, Andrea, Chris and Vittorio, on our paper that's called On the Importance of Appearance and Interaction Feature Representations for Person Re-identification. And this work was undertaken during our time at Huawei and IIT. So, Person Re-ID is a common task in surveillance applications. The idea is that given an image of a person of interest, and a gallery of images corresponding to different identities, we want to determine a match between the image and images within the gallery. And so today we're going to talk about two major directions that the Re-ID literature has undertaken. And the first is part-based models, which have performed consistently well in Re-ID. And the idea is relatively simple. So if you look at the image on the right-hand side, the idea is that we take the last convolutional layers of the backbone, such as a ResNet 50, and we duplicate them into three different branches. This gives us three different feature maps, which you can see in blue, and we perform different operations depending on the branch. So for the first branch, we just perform a global pooling to give us a feature representation. For the second branch, we can split it into partitions in the spatial and channel dimensions. And then on those partitions, we can perform some sort of pooling. And then for the third branch, it's similar to the second branch, but using three partitions instead of two. And this is from that paper that you can see in the bottom right, from a previous WACV conference. And so the aim of creating these partitions is to create local appearance representations that are more discriminative. And the idea is that the model is more robust because it has learnt how to identify individuals based on, for example, just the lower half of the image, or maybe just certain channels of the image. So there's a few limitations to this. One of them is that the computational cost is quite high because we have these three different branches. Another one is that the partitions are fixed a priori, and so there's no learnable element to it. Another major direction in Re-ID research has gone down the route of attention-based models. And the idea here is to incorporate a learning mechanism that's known as attention. And so I'm going to talk about channel attention here, for example. And so there's a few different blocks that have incorporated channel attention. One of them is the squeeze and excitation block. Another one is the global context or GC block. And the idea is that within these blocks, we want to model the interdependence between channels. And we do that using something like a 1x1 conv or a fully connected layer. And based on these learnable interactions between the channels, what we can do is we can selectively emphasize the discriminative features. And so this is one limitation of existing works, in our opinion. This idea that the channel attention vector is used to rescale or mix with the original features. In this work, we make the argument that actually this interaction information is complementary to the appearance-based features. And here I should say that when we say appearance-based features, what we mean is the spatial feature map. And when we say interaction-based features, what we mean is the channel attention. And so, as I said before, usually in previous works, or always in previous works, this interaction information is used to rescale or sum with the original appearance features. And of course, when you mix them together, you weaken the effects. And so what we suggest is that there are additional benefits to maintaining these representations separately and performing subsequent matching. And so the architecture that we use to do this, you can see on the right-hand side, we've called our network the Appearance and Interaction Representation Network, or AirNet for short. And we use parallel branches that specialize as an appearance expert and an interaction expert. And this is similar to the part-based models before, where we have global experts and then more local experts. So it's kind of analogous to that. And so what you can see is that we generate these representations, different representations based on appearance and interaction. And then you can see that we match them based on both of these feature representations. So again, here's AirNet in a bit more detail. And as I said before, we had parallel branches. And you can see the first branch here, which is the appearance expert. And the operation that we perform on the appearance expert is some sort of global pooling. So this is again similar to part-based models. In the second branch, rather than using something like partitions, what we do is we use a new attention-based pooling block, which models the interaction between the feature maps and then maintains this representation separately. So that's the key difference with existing attention-based blocks like squeeze and excitation block and also global context block. It's similar except for the fact that we do not mix with the original feature map. You can also see in the second branch that we include a global pooling as well. The motivation that we give for this is that if we want to model the interaction between the different channels, we must first build a representation of the features themselves. And so you can see that we have these three feature representations that we use individually for matching. So I think I've said a lot of this, but just diving into the attention-based pooling a bit more, we give, in the image on the right, you can see the global context block, GC block, on the right-hand side, which is the letter C. And you can see that we model the interdependency between the channels to give us an interaction feature representation. And then this is fused with the original feature map using something like a sum or a product. What we do in our attention-based pooling block is we maintain the interaction features separately for subsequent matching. Okay, so with this architecture, we perform some experiments on three popular benchmarks, so CUHK03, Market 1501, MSMT17, and for CUHK, it's split into labeled and detected. We use two different backbones, so a simpler backbone and a more powerful backbone, so the ResNet 50 and the ResNet 50 IBM. And in terms of metrics, we use mean, average, precision, and also rank 1, as is typical. And also we run our experiments 3 times and report the average results. So in terms of comparison with the state of the art, which you can see in the table at the bottom, our method outperforms across all data sets in the MAP metric, and it achieves the highest increase on the most recent, largest, and most challenging data set, which is MSMT17. So we achieve an improvement of 3.7% in that case. In terms of rank 1, we still do pretty well. We achieve the highest results for CUHK03 labeled and MSMT17, while falling just short in some of the other ones. So we also performed an extensive ablation study, and the idea was to evaluate the effectiveness of the multi-branch approach. And also we wanted to compare our attention-based pooling approach with other popular attention modules. And so in the table below, you can see that the baseline, which comes first, that's basically just a single branch model with global pooling. We replaced this global pooling with the attention-based pooling, and you can see that we get an improvement. We also replaced it with a GC, global context block, which is a popular attention block. And then from 4 to 6, you can see that we evaluated the approach of adding multiple branches. We replace our attention-based pooling with a global context block, and it gets worse results. And we also tried different variations of the global pooling. So, for example, with and without the global pooling in the second branch. But you can see that our architecture has the highest performance, AirNet. So we also visualized the saliency maps using the popular GradCam approach. And this GradCam method, it basically looks at places in the image that were important for classifying the identity. And so in the image on the right-hand side, you can see the original image. You can see the baseline model, which is the single branch model. And then the last 3 columns are for AirNet. And each of them is for the different feature representation. And so we have 2 branches. So AirNet 1 is the first branch, which is the appearance branch. And AirNet 2 is the interaction branch. And of course, we have 2A and 2B, where 2A is the global pooling feature representation, and 2B is the one that uses the attention-based pooling. And so what we see in this is that in the case of the interaction branch, which is AirNet 2B, it tends to focus on multiple discriminative small regions. And so in the case of the fourth row, for example, you can see it focuses on the head, the shoe, the bag, and the jeans. And so this reinforces the idea that the interaction feature representation focuses on the interaction between strong features, and that this is useful for discriminating between identities. Okay, so I'm going to conclude with some of our contributions. So in this current work, what we have contributed is a new multi-branch Re-ID model. And this multi-branch model has parallel branches where the first branch specializes as an appearance expert, and the second branch specializes as an interaction expert. Another contribution is a new learnable attention-based pooling block, which is used in the second branch of our model. And this differs from existing modules by the fact that the interaction features are not fused with the original feature map. And then finally, we show state-of-the-art results across 3 popular datasets and achieving quite highly in MSMT 17. Thanks for listening.